We're now going to discuss distributions and how they are estimated using R. Because distribution theory is the theory of distribution theory of distributions. You have understood it in the previous lecture, and now we're going to discuss how I'm going to demonstrate to you how distributions can be generated, estimated using R software. So unless you can estimate a distribution, it's a very limited use. Just knowing the distribution theory from a theoretical perspective has very limited applications. Being able to estimate distributions with real-time data is a skill that most people should develop. And R has a very good module which helps you to estimate distributions rather easily. Yes. So now we have the screen, we have the R software open, and as usual, we start with setting the work directory. We set the work directory, and this time we'll have to set a work directory, and I'll set the work directory right here in the Dropbox where we are working. Right, so I will open. So I'll copy the path, and then I will paste it over here. So the work directory is set. Now when I run it with Control R, the work directory has been created. I can check it by saying get work directory. And then I'm now working in this directory videos, which is in my Dropbox. Okay. Now we have been discussing there are broadly two types of distributions. One is a continuous distribution and the other one is a discrete distribution. So we'll start with continuous distributions, where I'll be showing you how the various distributions look like, how they can be generated, and how you can draw meaningful conclusions from the distributions. Then later on we will go into methods of estimating regressions with real-time data, and then trying to determine and what methods that we use to find out which is the most appropriate distribution that fits to data. So like I told you, every distribution is characterized by two parameters, and those two parameters have to be estimated from the data once the distribution is known. So all this we have done. So a random variable is a variable that is independent, where one observation of the data does not depend on its previous value, and therefore any data that follows that criteria follows a random distribution. And from the distributions, we can very importantly we can estimate what is the probability. The probability refers to what is the chance of an event occurring. Now the probability can be of making supernormal returns in the stock market. The probability can be what is the maximum I could lose in the stock market. So these are all issues related to probability which are very useful in decision making. So before we go into the applications of distributions with real-time data, we first have to understand how individual distributions are to be estimated, at least the principal ones. Now let us begin with the normal distribution. As you already know, the normal distribution is a continuous distribution and something that everybody assumes that the data follows. Now let me generate a data, call it norm. So in R you can do that. I can generate a normal distribution. Okay. And how I generate a distribution, I call it RNORM. So you can remember that. Follow the name of the distribution with R, not the complete, just norm. So I'll open a bracket. And they say, how many observations do you want? I want 10,000 observations. This is very useful in simulations as well. So then it wants to know, you want to generate a distribution with what mean? I want to generate a distribution with mean 123. And what is the standard deviation? 23.45. So with this command, I can generate a normal distribution. I can generate a normal distribution with the given parameters. So to generate a distribution with 1000 values, with 10,000 values, with 10,000 numbers, mean 123 and standard deviation 23.45. So it's very easy. So I can just generate it using this simple command. So norm, so the new variable will be called norm. The how it is to be generated is r norm 1000, mean 123, standard deviation 46. I run it. Okay, now the data has been generated. So now let me first see what is the dimension of this variable called norm. So I just say dim and I say norm. So I generate a norm. So let me just see what has happened. Okay, the data is there, but some of the dimension it doesn't. So sometimes dimensions don't come. So if it does not follow a data frame. So to convert norm into a data frame, so equal to same name. So what are you telling the computer? Create a variable, create a file called norm, which is a data frame. So it will look almost like an Excel sheet. So I run it. And now when I take the dimension, hopefully I'll get it done. Correct. So it wasn't a data frame. It was a vector. So I convert it into a data frame using the command data.frame and the name of the variable, which is norm. I could give this any name, but since I wanted it in the same name, so I called it norm. Now when I take the dimension, there are 10,000 rows, 1 column. Right. So we have a norm. So now let us see whether it follows a normal distribution. Now how do we do that? That is to plot. To plot. To plot a normal distribution, the command is just hist. So it's all lowercase. And then I will say no. So it's a very simple command, so I can visualize it. So it says the name is not numeric, so I'll just get the names of this variable norm. See what it is. So the names is only one variable called norm. Then I want to know what is the type, str. So I'll say norm and I'll run it. It's a number. So hist, unless it wants. Yeah, so it is not taking, normally it would, but here the name of the variable is norm. So then I always prefix it to the file name and I fit a distribution. I've got a normal distribution. Look, it's a nice and neat normal distribution. Okay, and okay, that did work. Okay, so we'll close it. So the command is just hist norm. Now if you want a smooth line, then I'll call it plot density. You may recall density $. So it gives me a smooth line. which gives me the probability. So the probability of the maximum value is a little more than 0.016. So now to recapitulate, what we do is we have generated a normal distribution. And to generate that normal distribution, we have taken a mean of 123 and a standard deviation of 23.45. Now let us check whether the data that was generated, what is its mean? So I'll say mean dollar. Okay, what is its mean? So mean is 122.94. Very close to this. And let us see the standard deviation. SD dollar. Okay. Standard deviation 23.6. Very close to this. So what you're trying, this is very useful in simulations. Supposing you want to simulate a data, you know the mean and standard deviation, and you don't have many observations, and you want to generate 10,000 observations, which follows a normal distribution, and the mean is 122.93 and standard deviation is 23.45. You can just do it in this fashion. Now there are many other properties. Now we know it follows normal distribution. Now let us look at this again. Now I want to find out what is the probability that this value will be less than 75. I want to know what is the probability that normally we use it in prices. So what do you want to know? I want to know what is the probability that the prices will fall below 75. I want to know what's the probability that prices will fall below 75. So please recall what we did in the earlier exercise where we used Excel to do this. So here what we do is you just say P norm. Okay, open a bracket. P norm. So so what is the probability that prices will fall below 75? That's a cutoff value, comma. It's asking what is the mean for a given mean, because this data has a mean of, precisely the data has a mean of 122.94. We should take this itself. Okay. And standard deviation of this. So I run it. And I get a value of 0.02. So which means that a value of 75. Okay, value of 75. 75 will have 2% of the area. Now let us take 100. Hi, come on. Hi, come on. Hi, good evening. Can I call you after 10 minutes? I'm doing a recording. I'll just call you after 10 minutes. 10 minutes I'll call you. Yeah, I'll just call you. So, okay. Now let us take the same distribution and I want to know what is the area below 100. What is the area below 100? So I can also, in this plot, I'll also say I'll just see if it works. So that's my distribution. This is my line that I want at 100. Yeah, very good. So this is how I create a line at 100. So my interest is to find out what is the area below this. In other words, I want to know what is it. I have a particular product which I sell in the market. I want to know what is the probability that prices will fall below 100. Now to give you a little more clarity on how this is done, first I did the plot density name of the variable, and here I added what is called as an AB line. V stands for vertical, H stands for horizontal. So vertical 100. So now I want to know what that is. So I'll use the same formula. Go to the next line, Control V, and then I'll find out what is the probability that prices will fall below 100. Right. Then I get a value of 16.5. So to continue this, so I do that, and then I do this. Then this area is 16.25, the same value that here. 16.54, 0.1654 is the area or the probability that the prices will fall below this or rainfall will be below this, the probability. So we can use a normal distribution for that. Now how to know whether this, so I know I can find out the probability. I can also find out what is the probability at 100. I want to find out what is this probability. What is the probability that this height? I want to find out this probability. I can see roughly it is 0.01. I can see that is roughly 0.01. But I want the exact value. And that's used a lot in actuary calculations, for which I will now find out. There's a slight variation. So this is to find out the probability. And this is to find out the ordinate. So the value that the only change that we, instead of P norm, you call it D norm. D norm. So D norm at 100. D norm at 100 with mean 0, standard deviation 60. So if this is the this is the probability. So 0.0105. So it gives you the height. So it gives you the height. So it gives you the height at that value. You know. So that is the thing. So I can find. So can you see, to generate the data it is R norm. To generate the data it is R norm. R norm. To get the probability it is P norm. To find out the probability below a given value, it's cumulative. In other words, to get the cumulative probability, it is P norm, and to get the probability at that level, it is D norm. And there's one more which is called Q norm, Q norm. So I want to know, given the probability 0.05, or I want to know 0.95 with the given mean and standard deviation. So I'll just copy this. Let's just copy this. They're all very simple. So Q now. So the value here, I give a probability. I want to know at 0.8. At 0.8, what will be the value? So I run it and I get a value 142. So to come back to this this thing, so it is 142. Okay, I want to find out at 5% probability what will be the value of 150. The next, what is the value if this is to be 5% probability? So there I use the Q norm. Now, and the Q norm, when we did Q norm, we got a value as 142.81. Now that I'll put it over here, 142.81. So please note what I'm doing. So AB line 142.82. Right. So just like I did earlier, now I'll get the line. Now this area is 5%, 80, 20%, 20%. This is 80. That's why we put 0.8. So please note what we did. AB. So we said Q norm 0.8 for this mean and this standard deviation. The cut value is 142 point something. 142.81. So we know that this is a very great property that we use to find out whether the data follows a normal distribution or not. This is what one is used. So this is a normal distribution, and another test of the normal distribution is the test of skewness and kurtosis. I discussed it earlier. So if I want to do skewness, and I'm not supposed to remember the command, so I'll say SKEWNESS. So it's an online help, so you don't need to be connected to the net to get this help. So I just run it, and it gives me the help, and it tells me how to. You can get it from Google also. So there are lots of skewness. So TSA skewness, agricole skewness. Anyone, you can take this agricole skewness. Agricole skewness means you just say skewness. First time must download this program called agricole. That is a convention in this thing. And then skewness, the variable. Okay, so I'll need the program. So I'll take this off. So I'll need the program called, I have to install it. Okay, so you'll have to install it once since I've already installed it, and to save time, I will just Control T and okay. So I'll run it since the program is already installed. I have no problem, and then it is skewness. Skewness. And the name of the variable is norm. Name of the file is norm, and the name of the variable is also norm. I get skewness of 0.005. And for a distribution to be normal, the skewness should be close to 0. In this is quite close to 0 because we have generated a normal distribution, and we should also have kurtosis. Okay. Kurtosis is also 0, but ideally kurtosis should have been 3, but that's not a real problem. But the real test of normality is this test of skewness. Ideally, skewness should be 0 and kurtosis should be 3. But this is not, so that again goes to the distribution of the data. So this kind of sums up the normal distribution. All variables are considered to be normally distributed, and therefore this is a fallacy sometimes because data need not be normally distributed. So the very laborious calculations that we did in Excel become so simple when you use R. So now I've generated a data. So now if I show you a data, I'll show, next I'll show you a data, and then we'll test whether the data follows a normal distribution. What is its mean? What are its parameters? We shall do that in a moment. Thank you.